So what we want to look at now is how do these carbonyl derivative reactions generally work? So if you have some nucleophile, and we usually think of nucleophiles as having a negative charge or at least a source of electrons like lone pairs, how are they going to react when they see one of these carbonyl derivatives? So acid chlorides, esters, amides. And typically what you're going to see is that the nucleophile is going to attack at the base of the carbonyl and push these electrons up. Now, if you remember, the reason this is so is that the base of the carbonyl tends to have some positive charge, right? Some positive character. And it's because the oxygens are more electronegative, right? So it's pulling the electron density towards the oxygen. So it allows our nucleophile to attack, push our electrons up. And so let's redraw that. We keep the R group because we haven't lost anything. So R group, remember, is any carbon chain. It can be hydrogen in most cases, in other cases as well. We put our oxygen. And now we had two lone pair to start. And with this arrow here in the red shows us that we're going to push the pi bond up onto the oxygen. And so we see that materialize as a lone pair. So now we've added our three lone pairs. This gets a negative charge. We still have the Y group. And that could be a chlorine, an ester, the oxygen portion of it. And we've also added our nucleophile. Alright, now what happens at this point is we have our tetrahedral intermediate, is that the lone pair can push back down. And the problem with this is we're going to reform the double bond, but we have 5 bonds to carbon. So we've got to lose something. So now we're going to lose the Y group. And so essentially what that does is it makes the Y group our leaving group. Alright, so it's the leaving group eventually. Alright, so what happens is this pops off, right? This group is going to leave. We remake a double bond here. So let's draw what that looks like. We've reformed the carbonyl. We only have 2 lone pairs on it. And now, where the Y was, our nucleophile has added plus Y minus. Right? If it was neutral, then it leaves with a negative charge. So, what we want to think about is, A, the nucleophile is going to attack the base of the carbonyl. Right? So the base of the carbonyl is our electrophilic spot, and that's where we're going to attack. Now, the other thing we want to look at is, how good is that Y group, our leaving group, at leaving? And if you remember from back last semester, things that are good leaving groups tend to be weak bases. Alright, so the better leaving group is going to be a very weak base. So if you think about this one, halogens tend to be good leaving groups. So for example, an acid chloride would be really reactive, right? Because this is a really good leaving group. Next on the chain would be an anhydride. If we kind of keep going with our reactivity series, we'd probably think about an ester, and then an amide. And now, what I want us to look at is, how good is the leaving group when it pops off? So let me highlight what's going to be our leaving group. In the case of the acid halide, it's going to be the chlorine. In the case of the anhydride, it's going to be this deprotonated carboxylic acid. Same thing here for the ether. It's going to be an oxygen with a negative charge. Here, a nitrogen with a negative charge. So let me just show you what happens when it pops off. You get a chlorine with a negative charge. Now, what you should think about in terms of thinking about which of these are going to be the best leaving groups, think about which is the weakest base. Right, so if you can think back to our acid-base chapter, whichever was the weakest base is going to be the best leaving group. So this is the weakest base up here. And then the strongest. And the way it works is whichever one is the weakest base is also the best leaving group. And so what happens is our leaving groups are best up here, and then they get worse as they go this way. So essentially what this is telling us is that acid chlorides are really reactive towards this reaction we just did. Anhydrides are pretty good, but not as good as acid chlorides. Esters work, not as good as anhydrides or acid chlorides. And then amides tend to be really tough to cleave. Okay? And so the bond that we're looking at cleaving in all of these is this bond here in between the carbonyl and either our chloride, our oxygen, or our nitrogen. And so if we're talking about reactivity, this one's the most reactive, and this one's the least.